Hey there, Janet Mapchick-Myers, and today we're looking at section 4.3 from the ZIL Intro to Differential Equations text, and this covers homogeneous linear equations with constant coefficients. So today we'll be checking out a cool method if you like algebra and finding roots, and it might be useful to maybe review the quadratic formula because we'll be talking about distinct real roots, repeated real roots, and conjugate complex roots. So recall from first order homogeneous differential equations in the form of ay prime plus by equal to 0. So this is a first order homogeneous DE. The coefficients a, which is not equal to 0, and b are constants. We can solve either by separation of variables or using an integrating factor. In this section, we'll check out how to use algebra to solve the differential equation. So if you consider ay prime plus by equal to 0, isolating ay prime, we would get negative by, and completely isolating y prime, we would get negative b over a times y. We could also take a look at that as y prime is equal to some constant k times y. Now, think about this. The only non-trivial function which has a derivative that is a constant multiple of itself is what? Beautiful. Y equals e to some m times x. For real values of x, this equation is only satisfied. So then we would have y is equal to e to the mx, right? Well, y prime would equal to what? Beautiful. M times e to the m times x. And then if you go from the formula we were using before, ay prime plus by equal to 0 would give us a times me to the mx plus b times e to the mx is equal to 0, which we could rewrite after factoring out e to the mx as a times m plus b as our other factor equal to 0. Cool, cool? All right, so since e raised to the m times x is never 0, right, for real values of x, this previous equation is only satisfied when m is a solution or root of the first degree polynomial equation a times m plus b is equal to 0. Because of the 0 property, either e to the mx would be 0 or am plus b would be 0. And since e to the m times x is non-zero, then am plus b must be the factor that is 0. So for this single value of m, y equal to e raised to the mx is a solution of the differential equation. In this section, we can use this procedure to produce exponential solutions for homogeneous linear higher order DEs. So that's where it'll kind of change course from what we learned before. What we learned before were just first order linear DEs, but now we can apply this to homogeneous linear higher order DEs. In the form of a sub n times the nth derivative of y plus a sub n minus 1 times the n minus first derivative of a y, continuing until you get to a2y double prime plus a1 y prime plus a0 is equal to 0. So still homogeneous. Where the coefficients a sub I, where I is equal to 0, 1, 2, all the way down to n, are real constants, and a sub n is not equal to 0. So then what we find is this auxiliary equation. So if you consider ay double prime plus by prime plus cy is equal to 0, where a, b, and c are constants, and if we let y equal to e to the mx, we have y prime would equal to, actually I'll kind of make it more of a sentence, we have y prime equal to m times e to the mx, and y double prime, sorry I'm a little sick if I sound weird, y double prime is equal to m squared e to the mx, just using the chain rule on that exponential derivative. So if you substitute into this equation we started with, right, we would have a times y double prime, which would be m squared e to the mx, plus b times y prime, which was me to the mx, plus c times y, which was e to the mx, is equal to 0. So all I did is substitute in y equal e to the mx and then the derivatives. So y prime was me to the mx, and then y double prime m squared e to the mx. Groovy? All right, so if I factor out e to the mx, we would have a times m squared plus b times m plus c as a factor, and that's all equal to 0. Well, we know that e raised to the mx is not 0, right? So a m squared plus bm plus c has to be the 0 factor. This last equation is called the auxiliary equation of the DE. So here and that's the DEAY double prime plus BY prime plus CY equals 0. Since the two roots are M equals, so I'm going to show you how to get the roots using the quadratic formula. So M would be the opposite of B, right, A, B, and C, plus or minus the square root of B squared minus 4 times A times C all over 2 times A. Rewriting as two different roots, we would get M1 could be called negative B minus the square root of B squared minus 4AC all over 2A. And then M2 could be the opposite of B plus the square root of B squared minus 4 times A times C all over 2 times A. Now, there's going to be three forms of the general solution for AY double prime plus BY prime plus CY equal to 0 corresponding to the three cases. So what can happen? Good. M1 and M2 could be real and not equal to each other. So we'll say real and distinct. And what does that mean about the discriminant? Remember, the discriminant for the quadratic equation is what? Awesome. So that would mean that B squared minus 4 times A times C is greater than 0. And another condition could be that we would get M1 and M2 are real and equal. So for them to be equal, right, meaning you would get one answer, then you would have to be adding or subtracting 0, correct? And so that means our discriminant would have to be equal to 0. Cool, cool? This is a 1. All right, and then lastly, M1 and M2 are conjugate complex numbers. And that occurs when B squared minus 4AC is negative, right? Or less than 0. And then you'll get some expression with I. Okay, so let's take a look at the three different cases. Distinct real roots. Well, when we have distinct real roots, under the assumption that the auxiliary equation has two unequal real roots, we find two solutions. The first one would be in terms of y equals e to the m1 times x. And that would be for y1. y2 would be equal to e raised to the m2 times x. We see that these functions are linearly independent, on minus infinity to infinity, and hence form a fundamental set. Therefore, the general solution on this interval will be, and you'll love this, y is equal to y1 plus y2, which would be some constant c1 e raised to the m1 times x plus c2 times e raised to the m2 times x. All right, now repeated real roots. So when m1 equals m2, we obtain one solution. So call it y1 equals e to the m1 times x. From the quadratic formula, m1 has to equal to negative b over 2a because the discriminant is 0, right? Since the only way for m1 to equal m2 is for b squared minus 4ac to equal 0. So a second solution of the equation using what we learned about in a previous section, okay, where instead of, going through the whole process, you were given a formula to find a second solution if you were given a first solution. We can find this second solution using this. So y2 is going to equal to e raised to the m1 at x, so I'm plugging in e raised to the m1 at x for y1 at x, okay? Now, times the integral of e to the negative integral. So what is my p of x? Well, if m1 is equal to negative b over 2a, right? Then 2m1 would equal to negative b over a, and negative 2m1 would equal to b over a. So that is what we put in for p of x. All right, and then continuing, we're integrating this with respect to x. That's all over y1 at x squared, so e raised to the m1 times x, the quantity squared, and then we're integrating that whole thing. So continuing, y2 will equal to e raised to the m1 at x, right? And then times the integral of e to the positive 2, e to the positive 2m1 times x after the integration, and the negatives get rid of each other, they turn positive, and then that is going to be over e to the 2 times m1 times x, right, from laws of exponents with respect to x. And what happens? These terms divide out to be 1, right? So y2, therefore, would be e raised to the m1 times x times x. Isn't that cool? So that, of course, is equivalent to y2 equals x times e to the m1 times x. And so it's really kind of a beautiful thing. You'll love this. The general solution is just e to the m1 at x, which was our y1, and we have our first constant with that, c1, and then plus c2 times x times e to the m1 times x. Isn't that amazing? So you'll love the problems we do. they're going to be, some of them anyway will be a lot more easy as long as you understand the auxiliary equation than what we've been dealing with. Okay, case 3, conjugate complex roots. If m1 and m2 are complex, then we can write m1 is equal to some alpha plus I times a beta. And then the other one, because you have to have the conjugate, would be m2 is equal to alpha minus I times beta, where alpha and beta, which has to be greater than 0, are real, and I squared, of course, is -1. So this will be a similar format as case 1, where we had 2 roots that were distinct, okay? But this time, we'll have y is equal to c1 e raised to the alpha plus I times beta x plus c2 times e raised to the alpha minus I times beta x. Now, this is fine, in form, but in order to work with real numbers instead of complex numbers, we're going to use Euler's formula. And it's a really cool trip down memory lane for Calc 2. So I thought it would be fun for you to see the derivation of this. So here we go. And by the way, Euler's formula is E raised to the I theta is equal to cosine theta plus I times sine theta, where theta is any real number. So it's derived from the Maclaurin series, e to the x equal to the summation. So if you remember with the Maclaurin series, your power series is centered at 0, and n goes from 0 to infinity, and then it's x to the n over n factorial. So let's check this out, all right? So first of all, we have I, we have theta, and you can see from the formula that you're going to end up with cosine theta and sine theta in there. I would be a multiplier to sine theta. So let's look at the trend of these different, these patterns. So first, if we kind of check out the patterns for I, all right? So I to the 0 is 1, right? I to the 1 is I. I squared is -1. I cubed is going to be what? I squared times I, which will be -I. And now I to the 4th tends back to what? Beautiful. 1, because you'd have -1 times -1, which is 1. So for the powers of I, they repeat 1, I, -1, -I, and 1. All right? So that's the first step here. Now, next step, the series e to the theta, okay? E to the theta is going to be the same as the e to the x one, but we're going to put thetas in there, all right? So e to the theta would be theta to the 0 over 0 factorial plus theta to the 1 over 1 factorial plus theta squared over 2 factorial plus theta cubed over 3 factorial plus theta to the 4th over 5 factorial. I'll take it just a little bit longer, plus theta to the fourth over 4 factorial, my bad. And theta to the 5th over 5 factorial, theta to the 6th over 6 factorial, plus ... Now, what is that? That gives us e to the theta is 1, because remember 0 factorial is 1, plus theta squared over 2 factorial, I'll leave them in factorials, plus theta cubed over 3 factorial, plus theta to the 4th over 4 factorial, plus theta to the 5th over 5 factorial, plus theta to the 6th over 6 factorial, plus ... All right, now let's check out sine theta, that series, okay? So the power series, the Maclaurin series for sine theta is equal to theta minus theta cubed, and you can look these up, over 3 factorial, plus theta to the 5th over 5 factorial, minus theta to the 7th, so it's an alternating series, over 7 factorial, plus minus ... So notice it only has the odd powers, right? Along with the odd factorials, and the signs alternate. So this would be the, term 0. So that's n equals 0. N equals 1. N equals 2. N equals 3. So on the odd terms of the series, you've got a negative sign. Cool? All right. Now, let's take a look at cosine theta. So cosine theta, it turns out, ends up being the evens, okay, which will include the 0th term of the e to the theta series when we circle back to it. So it's going to be 1, okay, minus theta squared over 2 factorial, plus theta to the 4th over 4 factorial, minus theta to the 6th over 6 factorial, plus minus ... So for this series, this is the n equals 0 term. You've got your n equal 1 term next, n equal 2, n equal 3. So again, at the odds, you've got negative signs, right? The odd terms of the power series, you have negatives. So let's put it all together, all right? So now, if you recall, when you have a power series that you know, and it's got a multiplier to that power that is not part of the summation, right? Then it just goes in with the x, or the theta in this case. So if I come back here and I look at my e series, but instead of putting in e, I put in e to the I theta, right? This ends up being I theta raised to the 0 over 0 factorial, plus I theta to the 1 over 1 factorial, plus I theta squared over 2 factorial, continuing, go a little bit further. So it would continue in that format, okay? So now what's going to happen is this. We follow the trends for I. So e to the I theta is going to be, 1, right? And then we will have plus I theta over 1 factorial plus I squared theta squared, but I squared is negative 1, right? So that'll make this alternate. So we'll have minus theta squared over 2 factorial. So notice 1 was our first one. I was our second one. Negative 1 is our third one. Now we're going to have minus I theta cubed over 3 factorial. That's this guy. And then it's going to go where? Back to where it started, right? So we'll have plus 1 theta to the 4th over 4 factorial. Continuing, plus I theta to the 5th over 5 factorial. So our next one here is going to be negative 1. So we would have minus 1 theta to the 6 over 6 factorial plus minus dot dot dot. So remember that you can commute terms. I mean, a power series is just a sum, right? So let's rewrite this power series with the real terms together and the imaginary terms together. So what you'll see, it's really cool, is that you'll get 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial, minus theta to the 6 time to get up, I guess, over 6 factorial plus minus dot dot dot, and then, so that's one of them, and then we're going to add the terms with I. So we'd have I theta over 1 factorial, right? And then minus I theta cubed over 3 factorial plus I theta cubed I did the cube, plus I theta to the 5th over 5 factorial minus plus dot dot dot. And when I put them together, it's beautiful because e to the I theta is going to equal to cosine theta is the purple. When you add to that, factoring out the I, you would get I sine theta because the I is not part of the summation. So it can be factored out. Isn't that awesome? Anyway, so that is Euler's formula, which is amazing. And so now let's take a look at what we can do. So with this information, we can take a couple of things and check them out. So we can take, how much room do I have down here? So we can take E to the I times beta x. That's going to equal to cosine beta x plus I sine beta x. So it's the same idea, okay, as what we were doing before. Instead of just having an I times theta, we have an I times beta times x, all right? And so now if we look at e to the negative I times beta x, that's going to equal to cosine at negative beta x plus I times sine at negative beta x. Well, recalling from our negative angle identities, the cosine of a negative angle is just itself because it's an even function, so you get cosine at beta x. And then sine is an odd function, so we would get minus I times sine at beta x. Cool so far? Now, what the heck? Let's add those together, all right? So we're going to add e to the I beta x plus e to the negative I beta x. Now that's going to equal to cosine beta x plus I times sine beta x, and then plus cosine beta x minus I times sine beta x. And where we're going here is, remember, we can work with those linear combinations, right, for solutions. So when we do that, what happens? The I sine beta x's zero out, and we end up getting two of these cosine beta x's. Cool so far? Now let's go the other way. E to the I times beta x minus e to the negative I times beta x will be cosine beta x plus I sine beta x minus cosine beta x minus I sine beta x. This time, it's the cosine beta x's that's zero out, and we'll get two of these I times sine beta x's. Good so far? Awesome. All right, now, since y is equal to C1 times E alpha plus I times beta, all that times x, plus C2 times E to the alpha minus I times beta, all that times x. This is a solution of ay double prime plus by prime plus cy equal to 0 for any choice of constants C1 and C2. We can be strategic, right, for these two things. So we can say that for y1, we could let C1 equals C2 equal to 1, all right? And that would give us that y1 could be equal to e to the alpha plus I beta times x plus e to the alpha minus I times beta, all of that times x. And for the other one, we can let C1 equal to 1 and C2, C equal to -1. Well, that's going to give us what? Y2 would equal to e to the alpha plus I beta, all that times x, minus e to the alpha minus I beta times x. But let's check this out. We have our expression for y1. Now, notice that if I multiplied x through, I would have alpha x plus I beta x. So that would be e to the alpha x times e to the I beta x. And similarly here, we'd have alpha x minus I beta x if I distributed the x through. So we would end up having y1 is equal to e to the alpha x times e to the I beta x plus e to the negative I beta x. But what did we find out that was earlier? Beautiful, it's this guy here, right? So we would get our e to the alpha x times 2 cosine beta x. And what about y2? Factoring out using similar reasoning, e to the alpha x, we would have e to the I beta x minus e to the negative I beta x. But what was that? That was equal to, you'd have your e to the alpha x as a multiplier times 2I times sine beta x. So, prettying them up, 2 times e to the alpha x cosine beta x. The second one, 2I e to the alpha x times sine beta x. Well, a constant multiple of a solution of a homogeneous linear DE is also a solution, right? So it turns out that y would equal to just taking these parts, whoops, here, and then putting the general constants with them, we would have y would equal to C1 e to the alpha x times cosine beta x plus C2 e to the alpha x times sine beta x. And factoring out the e to the alpha x, we would just get C1 times cosine beta x plus C2 times sine beta x. So here we go. You'll really appreciate this. So this is like what you want to take away from this one. All right. So actually, let's sort of go through our takeaways here. So this one is what we would want for our complex roots. Okay. And then way back here, this would be our takeaway for our, over here, sorry. This would be our takeaway for our roots with multiplicity greater than or equal to 2. And then this one is our takeaway for real roots that are distinct. And you could have combinations of all these types of answers. Cool? All right, so now example 1. Find the general solution of the given second order DE. You'll love this. What should we do? Well, find the auxiliary equation. So what's our auxiliary equation? Beautiful. M squared minus 10m plus 25 equal to 0. This factors as the quantity m minus 5 squared equal to 0. So you would have a root of m equal to 5 with multiplicity 2. Good so far? So m1 equals m2 equals 5. So our general solution is going to follow that second case, our second highlighted area here. So the first one we would have just c1 e to the m1x, and then you multiply the next one by x. So we'd have y equals c1 e to the 5x plus c2 times x e to the 5x. And that's our general solution. Isn't that beautiful? All right. So, coming back to this guy, well, what's going to happen? Auxiliary equation. So, 2m squared plus 2m plus 1 equals 0. So for this one, I'm not seeing where it's going to factor real quick, so I'm just going to run right in there and do the quadratic formula. So m is equal to the opposite of b, which is the coefficient to the m term. So negative 2 plus or minus the square root of negative 2 squared minus 4 times a, which is also 2, times c, which is 1, all over 2 times a. M equals negative 2 plus or minus. Well, we'll get 4, positive 4 minus 8, so we'll have square root of negative 4 all over 4. And so m will be equal to negative 2 plus or minus, careful, 2 times I, don't just ignore the negative, all over 4. Now we can reduce that to be m equals negative 1/2 plus or minus 1/2 times I. So letting m1 equal to negative 1/2 plus 1/2 I, and m2 is the conjugate, negative 1/2 minus 1/2 I. Which answer applies? Well, the only one that had imaginary things that going on with it was this guy here, where you have e to the alpha x, and the beta is going to go along with the angle x. It's a multiplier to the angle. So remember, this is the original format right here and right here. Remember, we got the format here for our answers. Cool so far? So alpha has to be what? So if you match it up to So therefore, alpha must be beautiful negative 1/2, right? And then beta is positive 1/2. Cool, cool? So that means our general solution is y equals e to the alpha x, so negative 1/2 x, times c1 times cosine beta x, so 1/2 x, plus c2 times sine beta x, which would be 1/2 x. And we're done. Isn't that awesome? So on our next exam, you'll be able to have notes. So make sure you've got these notes, okay? All right, meaning the formulas. All right, let's now look at an initial value problem, okay? So here, this, remember, is just like y double prime, right? So first we need to solve that homogeneous, right? So we're missing a y prime. So if you think about it, your A is 1, your B is 0, your C is equal to 1. That's the coefficient to the y. So you have a 1 in front of the double prime, a 0 in front of the prime, and a 1 in front of the y. And we'll ignore that initial value stuff until later. So I'll just rewrite it as y double prime plus y equals 0. And our auxiliary equation is m squared plus 1 is 0. So m squared is negative 1. And so m equals plus or minus the square root of negative 1, which is plus or minus I. Now you could write m1, if you wanted, as 0 plus 1i, and m2 would be 0 minus 1i. So alpha is 0, beta is 1. Cool so far? So your general solution would be e to the 0 times x. Oh, sorry, we're dealing with theta, not x. 0 times theta, and then times c1 cosine of 1 theta plus c2 sine of 1 theta. So when you simplify that, you'll just get e to the 0, which is 1. So y is just going to be c1 cosine theta plus c2 sine theta. Cool, cool? Now let's apply those initial conditions. So we need to have, we have y at pi over 3 is equal to 0. And then y prime at pi over 3 is equal to 2. And so now let's see if we can use those to solve for our constants, right? Because we have y, we do need to find y prime, right? So first let's apply that initial condition to y. So y at pi over 3 would be c1 times cosine at pi over 3 plus c2 times sine at pi over 3. And then y at pi over 3 was given to be 0. So I'll put the 0 in place on the left-hand side. And then finding cosine at pi over 3, that's just going to be 1/2. And then sine at pi over 3 is the square root of 3 over 2. And so we have this situation here, right? And let's look and see what y prime is. So y prime now will be equal to negative c1 times sine at theta plus c2 times cosine at theta. Y prime at pi over 3 is negative c1 sine at pi over 3 plus c2 times cosine at pi over 3. And it was given to be 2, so I'll substitute in 2 on the left. And then we'll have negative c1 times root 3 over 2 plus c2 times 1/2. Cool so far? All right. Well, working with this purple equation over here, we can get that. Now, if I multiply both sides by 2, gets rid of those denominators, and I'll get 0 is c1 plus root 3 c2. So c1 is negative square root of 3 times c2. Plugging that into the green equation over here, we would get 2 is equal to negative a root 3 c2. I put that all in for c1, and then there's still a root 3 over 2 hanging out, right? And then plus 1/2 c2. Again, multiplying everything by 2 just to clear out the fractions. We would have 4 equals root 3 c2 times root 3 plus c2. 4 would equal to 3 c2 plus c2. 4 would equal to 4 c2. And 1 would equal to c2. So if c2 is equal to 1, then c1 is going to be negative root 3 times 1, which is negative root 3. So at the end of the day, we would end up with y equals negative root 3 times cosine theta plus sine theta. And we're all done here. Isn't that amazing? I love this section. All right, let's continue. So now higher order equations. So when we start discussing these, we want to look at solving an nth order differential equation, a sub n y, the nth times the nth derivative of y, plus a sub n minus 1 times the n minus first derivative of y, plus dot dot dot, plus a2 y double prime plus a1 times y plus a0 equals 0, where the I equals 0, 1, 2, dot, 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 all the way to n are real constants. So to solve this, we must solve an nth degree polynomial equation, a sub n m raised to the n plus a sub n minus 1 times m to the n minus 1 for our auxiliary equation, plus dot 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 plus a2 times m squared plus a1 times m plus a0 equals 0. If all the roots of this equation are real and distinct, the solution will be y equals c1 e raised to the m1 times x plus c2 times e to the m2x all the way down until you get to cn times e to the m sub n x. Now, it's harder to summarize how cases 2 and 3 apply here because the roots of an auxiliary equation of degree greater than 2 can occur in many combinations. So if you think about it, when m1 is a root of multiplicity k of an nth degree auxiliary equation, the linearly independent solutions are going to be e to the m1x comma xe to the m1x comma x squared e to the m1x, continuing until you get to x to the k minus 1 e to the m1x. Cool so far? And then the general solution has to contain the linear combination, so this is just the other side of y, c1 e to the m1 times x, and then plus c2x times e to the m1 at x, plus c3 x squared e to the m1x plus dot 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 plus, and now you would get to c sub k. The x would be raised to the k minus 1 because of the constant term, potentially, and then you would have e times e to the m sub 1x. Remember that when the coefficients are real, complex roots of an auxiliary equation always occur in conjugate pairs. So if you had like a fifth degree equation, right? So a fifth degree auxiliary equation could have 5 distinct real roots. It could have 3 distinct and 2 complex roots. It could have 1 real and 4 complex. It could have 5 real but equal. Roots. I mean 2 real but equal, so multiplicity 2, and one other real, and two complex, etc. So that's why it's not going to be summarized. But you make a linear combination of that. So example 3, find the general solution of the given higher order differential equation. So we've got y triple prime minus 6y double prime plus 12y prime minus 8y is 0. The auxiliary equation is m cubed plus minus 6m squared plus 12m minus 8 is equal to 0. So you could go and look this up on technology. I thought for fun, you could see why in the world you even learned about possible rational zeros in your pre-calc class. If you want to fast forward through this, you can. But possible real zeros, or possible rational zeros, I should say, are found by looking at what your A0 and your leading term and your constant term. So your leading term A sub n is equal to 1. Your constant term A sub 0 is equal to negative 8, right? So P consists of the possible factors of negative 8. Integer factors of negative 8. So you would have plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. Q are the possible factors for 1, which are just plus or minus 1. The possible rational zeros will be the ratio of all of these, right? So the possible P over Q are plus or minus 1 over 1, which is just plus or minus 1, plus or minus 2 over 1, plus or minus 2, and so on. So these are all the possible rational zeros. So then what a person does is they use long division, polynomial long division or synthetic division to see if they can find a factor, right? So you usually, I start with something low, 1, plus or minus 1, plus or minus 2. So you're looking at the thought where x minus c is what you're working with. So keeping that in mind, you just list the coefficients of the polynomial, which are 1, negative 6, 12, and negative 8. You draw a line under it. You put your c in a little box, and we'll just try c as 1. The first term drops down automatically. 1 times 1 is 1. Negative 6 plus 1 is negative 5. And you just keep going. So we would get positive 7 here. 7 times 1 is 7. Now this represents the remainder. This is not going to equal to 0, so 1, c equal to 1 is not a factor. Try negative 1. So this is our first attempt. Didn't work. Second attempt. One times negative 1 is negative 1. We would get a negative 7 here. 7 is what you get when you multiply it to negative 1. So this becomes 19. Negative 19. This will be negative, 27? 26? 27. So this remainder is not 0, so negative 1 is not a factor. All right, let's try 2. Bringing down the 1. 1 times 2 is 2. We'll get a negative 4 when we add that to negative 6. Negative 8. We get a 4 here. And then, woo, we got it. So basically, what did we find? We found out that x minus 2 is a factor of the polynomial. So it turns out that the left-hand side can be written, the degree of each of these. So basically, what did we find? We found that m cubed minus 6m squared plus 12m minus 8 divided by m minus 2 is equal to, the degree goes down by 1, so you'd have m squared minus 4m plus 4. Cool, cool? So up here, we can put the factored form that we just found. So we got that this is equal to m minus 2 times m squared minus 4m plus 4. That's going to equal to 0. We can further factor. This is the quantity m minus 2 squared, but we now have 3 factors of m minus 2. So we'll get the result of m equals 2 with multiplicity 3. And what does that mean? That means that y will equal to c1 times e to the 2x plus c2 times xe to the 2x plus c2 times c3 times x squared e to the 2x. And we're done. Isn't that awesome? All right, so I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please hit that like button and subscribe. Bye.